Right now, as you read this, the night sky above you contains approximately 5,000 stars visible to the naked eye. 5,000 points of light scattered across the darkness, each one burning with a fury so immense that no human language was built to contain it. The nearest of them beyond our own sun is so far away that the light reaching your eyes tonight left its surface over 4 years ago. The farthest ones you can see departed their source centuries before you were born. Every single one of them is dying, not metaphorically, not poetically, in the most literal physical sense that science can describe. Every star you have ever seen, every star that has ever been named, catalogued, worshipped, or navigated by, is a controlled explosion in the process of consuming itself. A temporary balance between the inward crush of gravity and the outward roar of nuclear fire. And that balance, without exception, always ends. But here is what most people get wrong when they hear that. They imagine the death of stars as a distant concern, a problem for astronomers for the far future, for civilizations that will come long after we are gone. They hear the word entropy, the slow, inevitable slide of all energy toward disorder, and they file it away as an abstraction, something that happens to other things in other times. The real explanation is far more unsettling than that. The death of stars is not a distant event. It is the present condition of the universe. It is happening right now above your head, in every direction you could point your finger. The cosmos you live inside is not young and vibrant and endlessly generative. It is by almost every measure that physics can offer already past its peak. The rate at which new stars are being born has been falling for 10 billion years. The universe is not in its morning. It is somewhere in a long, slow afternoon, and the evening, if you can call it that, will last longer than the mind can hold. If you enjoy journeys that take you to the very edge of what is known, that strip away the comfortable illusions we carry about time and existence, and leave you standing in the cold clarity of the cosmos, do me a small favor and hit that like button and subscribe to this channel. It genuinely helps this reach the people who need it. And I think if you have come this far, you are one of them. Get yourself comfortable. We are going to travel to the end of everything. Let's begin. To understand where the universe is going, you first have to understand where it came from. Not in the vague, gestural sense that most people carry with them, the Big Bang, an explosion, stars forming, here we are, but in the precise, almost violent sense that cosmology actually describes. Because the beginning of the universe was not an explosion in the way you picture one. It was not a detonation in empty space. There was no empty space. There was no space at all. Approximately 13.8 billion years ago, everything that exists, every atom, every force, every dimension of space and time was compressed into a state of unimaginable density and temperature. Physicists call this the initial singularity, though the word singularity here is almost an admission of defeat. It means the mathematics breaks down. We cannot see past it. Whatever existed before that moment, if before even has meaning, in a universe where time itself had not yet been born, is beyond the reach of any tool we currently possess. What we do know is what came after. In the first fractions of a second, intervals so small they make a nanosecond look like an eternity, the universe underwent a period of expansion so rapid it strains the word expansion to breaking point. Physicists call it inflation. In a time span shorter than 10 to the power of negative 32 seconds, the universe grew by a factor of at least 10 to the power of 26. If you took a single proton and inflated it at that rate, it would become larger than the observable universe is today. Larger. In less than the blink of anything. And then inflation ended. The energy driving it converted into a seething plasma of particles and radiation. The universe was hot, incomprehensibly violently, hot somewhere around 10 to the power of 27 degrees Kelvin. At that temperature, not even atoms could exist. Matter and antimatter flickered in and out of existence, annihilating one another in a fury of energy. For reasons that physics still does not fully explain, matter won that war by a tiny margin. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. The billion pairs annihilated. That one leftover particle multiplied across the entire universe is everything you have ever seen or touched. You exist because of a rounding error at the dawn of time. For the next 38,000,000 years, the universe remained opaque. Think of it as a wall of white-hot fog so dense that light could not travel more than a short distance before being absorbed and re-emitted over and over in every direction. The universe was bright, but it was not transparent. No photon could travel freely. The entire cosmos was a plasma, a churning soup of protons, electrons, and radiation, all tangled together in a state of perpetual interaction. And then something changed. As the universe expanded, it cooled. After 3,800,000 years, the temperature dropped to roughly 3,000 degrees Kelvin hot, but no longer hot enough to keep electrons stripped away from protons. The electrons slowed. They were captured. Hydrogen atoms formed for the first time, and in the span of what cosmologists call recombination, a process that took perhaps 100,000 years, which is an eye blink by cosmic standards, the fog cleared. Light for the first time in the history of existence could travel freely. The photons that had been trapped in that plasma for 3,800,000 years flooded outward in every direction. That light is still traveling today. You are bathed in it right now, though you cannot see it. It has been stretched by the expansion of space from visible wavelengths down into microwaves, cooling from 3,000 degrees to just 2.73 degrees above absolute zero. It is called the cosmic microwave background, and it is the oldest light in the universe. A photograph of the universe at 3,800,000 years old, still arriving at your skin every second of your life. But in those first moments after the fog cleared, the universe was dark in a different way. The light existed flooding everywhere, yet there were no stars, no galaxies, no sources of new light. Just vast clouds of hydrogen and helium gas drifting in the darkness, shaped by tiny variations in density left over from inflation, variations smaller than 1 part in 100,000. An almost perfectly smooth ocean of gas with barely perceptible ripples. Those ripples were enough. Gravity is patient in ways that nothing else in nature is. It does not rush, it does not tire, it simply pulls ceaselessly with every atom on every other atom, across every distance. Over millions of years, the slightly denser regions of that primordial gas began to pull in material from the surrounding space. Slowly, then faster still, the gas collapsed inward. The pressure at the center of these collapsing clouds grew, the temperature climbed, and then in the universe's first few 100 million years, in a period astronomers call cosmic dawn, something happened that had never happened before. Fusion ignited. The first stars were nothing like the sun. They were monsters. Astronomers call them population 3 stars, and they were composed almost entirely of hydrogen and helium because those were the only elements that existed. No carbon, no oxygen, no iron. Just the lightest elements in the periodic table collapsed under their own gravity into objects that burned hundreds or even thousands of times hotter than the sun, and were anywhere from 10 to 1,000 times more massive. These stars were extraordinary, and they were brief. A star like our sun will burn for approximately 10 billion years. The most massive population 3 stars burn through their fuel in perhaps 1 million years, maybe less. By stellar standards, they were sparks, brilliant, violent, and gone almost before they began. When they died spectacularly in explosions called supernovae that scattered their material across enormous distances, and in the cores of those dying stars, and in the violence of those explosions, something new was created for the first time in the universe's history. Heavy elements, carbon, oxygen, silicon, iron, calcium, the periodic table being written one stellar death at a time. Every element heavier than hydrogen and helium that you have ever encountered, the iron in your blood, the calcium in your teeth, the oxygen in every breath you take, was forged inside a star that died before the Earth existed. You are not just made of star stuff in the poetic sense that Carl Sagan meant. You are made of the ash of the universe's first fires, the literal nuclear residue of stellar explosions that happened when the cosmos was still finding its shape. The second generation of stars, population 2 stars, formed from clouds seeded with those heavy elements. They were still ancient, still different from the stars we see today, but richer, more complex. The universe was diversifying. The first galaxies were assembling small and irregular colliding, and merging in slow gravitational dances that played out over hundreds of millions of years. The cosmic web was beginning to take shape, filaments of dark matter providing the scaffolding along which gas and stars gathered. And then came the third generation population I stars. Stars like our Sun, metal-rich, relatively cool, long-lived, orbited by the rocky planets that the earlier stellar generations had made possible. Our solar system formed approximately 4.6 billion years ago from a cloud of gas and dust that was itself a remnant of earlier stellar deaths. The Sun ignited, the Earth coalesced, oceans formed, and in those oceans in chemistry so complex it still defies full explanation, something extraordinary assembled itself from the available materials. Life that would, after 4 billion years of evolution, through extinction and adaptation and accident, produce a species capable of looking up at the night sky and asking, how did all of this begin? And the question we are here to answer tonight, how does all of this end? To feel the weight of where we are in cosmic time, you need a way to hold it. Numbers alone are not enough. 10 billion years, 13 billion years, these figures pass through the mind without leaving a mark. So consider this instead. Compress the entire 13.8 billion year history of the universe into a single calendar year. January 1st midnight is the Big Bang. December 31st midnight is right now, this moment as you listen to these words. On that scale, the cosmic microwave background that first light released when the fog cleared appears in the first hours of January 1st. The first stars begin to form somewhere in mid-January. The Milky Way takes shape around mid-March. Our Sun ignites on September 2nd. The Earth forms on September 6th. Life appears on Earth around September 21st. Dinosaurs walk the planet on December 26th. They go extinct on December 30th. The entire history of modern humans, every civilization, every empire, every recorded word, every scientific discovery unfolds in the last 14 seconds of December 31st. You are here in those final seconds looking back at the whole year, and here is what that scale reveals. The universe has been building toward complexity for the vast majority of its existence. The formation of stars, the synthesis of elements, the assembly of galaxies, the emergence of life, all of it happened in what is, cosmically speaking, a sustained creative period. The universe was for most of its history generative, producing new structures, new complexity, new light. But that creative period has a shape, and the shape is a curve that peaked and is now declining. This is the fact that most popular accounts of cosmology quietly omit. The universe's star formation rate, the rate at which new stars are being born across all galaxies, reached its maximum approximately 10 billion years ago, when the cosmos was roughly 3 billion years old. Astronomers call this period cosmic noon. The universe was dense with gas, rich with the material needed to form stars, and galaxies were colliding frequently, triggering enormous bursts of new stellar birth. It was, in every sense, the most luminous moment in cosmic history. Since then, the rate has been falling. Today, the universe forms stars at roughly 1/30th the rate it did at cosmic noon. The gas that feeds star formation is being consumed faster than it is being replenished. Galaxies that were once bright, active, churning factories of new suns are aging, quieting, their star-forming regions dimming as the raw material runs out. Our own Milky Way forms perhaps 1 to 3 new stars per year. A billion years ago, it was forming 10 times that many. The universe is winding down, not catastrophically, not suddenly, but steadily, measurably, in a direction that has only one destination. There is a force accelerating this process. Discovered in 1998, it was confirmed by 3 astronomers, Saul Perlmutter, Brian Schmidt, and Adam Rees, who were awarded the Nobel Prize in Physics for the finding. They were studying distant supernovae, using those stellar explosions as cosmic measuring sticks, expecting to find that the universe's expansion was slowing down under its own gravity. What they found instead was the opposite. The expansion of the universe is accelerating. Something is pushing space apart faster and faster with every passing moment. Physicists call it dark energy, though the name is more an admission of ignorance than a description. We do not know what dark energy is. We know what it does. It makes up approximately 68% of the total energy content of the universe. and it is causing the fabric of space itself to stretch at an ever-increasing rate. The consequence of this is not merely that distant galaxies are moving away from us, it is that there is a horizon, a cosmic horizon beyond which galaxies are moving away faster than light, not because they themselves are moving at superluminal speeds that would violate relativity, but because the space between us is expanding so rapidly that the light they emit can never cross the growing distance to reach us. Those galaxies are, for all practical purposes, gone. We will never receive another photon from them. They have passed beyond the edge of our observable universe, and with every second that passes, more follow. Right now, the observable universe contains approximately 2 trillion galaxies. In 2 billion years, as Andromeda begins its final approach toward the Milky Way, many of those galaxies will already have dimmed beyond detection. In 100 billion years, roughly 7 times the current age of the universe, the only galaxies remaining within our observable horizon will be those gravitationally bound to us in the local group. Everything else will be gone, not destroyed, simply unreachable, separated from us by an expanding void that light itself cannot cross. Imagine standing in a city at dusk. The lights are coming on all around you, thousands of them stretching to the horizon in every direction. Now imagine that the city is expanding, not the buildings moving, the ground itself stretching. The lights farther away begin to recede. Over years, the ones on the horizon disappear. Over decades, you can see fewer and fewer. The city is still there somewhere beyond what you can see, but you will never reach it, and its light will never reach you again. This is what is happening to the universe right now, quietly, without announcement. A civilization that arose in 100 billion years on a planet orbiting a star in the local group would look out at a sky nearly empty of galaxies. They would see their own small cluster of light, and beyond it, in every direction, darkness. If they had no record of what came before, no ancient astronomical data, no inherited maps of the universe, they would have no way of knowing that 2 trillion galaxies once filled the sky. They would conclude, using the best science available to them, that the universe consisted of a single island of stars surrounded by an eternal void. They would be wrong, but they would have no way of knowing it. We are the lucky ones. We live in the one era of cosmic history, when the full scope of the universe is still visible to us, when the light from its most distant reaches is still arriving, when the evidence of its origin and structure is still accessible. That window is already closing. The fact that you can look up at the night sky tonight and see light that has traveled for billions of years across a universe, still rich with structure, that is not a given. It is a privilege specific to this moment in time, and it will not last. The stars you see tonight exist across an enormous range of ages and sizes, and understanding that range is the only way to understand how long the light will last. We tend to imagine stars as similar things, spheres of burning gas, differentiated mainly by brightness and color. But the differences between the smallest and largest stars are so extreme that they barely seem like the same category of object. A red dwarf star and a blue Hypergean star are both technically stars. They are also about as similar as a candle flame and a volcanic eruption. This distinction matters enormously when we talk about the end of stellar light in the universe, because the death of the last star is not one event. It is a process that will unfold across a time span so vast that the current age of the universe, all 13.8 billion years of it, will be a rounding error at the beginning of the calculation. Begin with the giants, the most massive stars in the universe. Objects containing anywhere from 8 to several hundred times the mass of our Sun live lives of extraordinary brevity and violence. A star with 30 times the Sun's mass will burn through its entire hydrogen fuel supply in perhaps 8 million years. A star with 100 solar masses may last only 3 million years. These are enormous objects, luminous enough that a single one outshines entire stellar clusters, burning so furiously at their cores that the pressure and temperature required to sustain fusion destroys them from within almost as quickly as gravity can build them up. When these massive stars exhaust their hydrogen, they do not simply cool and fade. They evolve rapidly through a sequence of increasingly desperate fusion reactions, burning helium into carbon, carbon into oxygen, oxygen into neon, neon into silicon, silicon into iron. Each stage is shorter than the last. The hydrogen burning phase lasts millions of years. The final silicon burning phase, which produces the iron core that will trigger the star's collapse, lasts approximately 1 day. Iron is where fusion stops. Unlike every lighter element, fusing iron absorbs energy rather than releasing it. When an iron core accumulates in the heart of a massive star, it reaches a critical mass roughly 1.4 times the mass of the Sun, a limit known as the Chandrasekhar limit, named for the Indian-American astrophysicist Subramanian Chandrasekhar, who derived it in 1930 at the age of 19 on a steamship from India to England, using nothing but mathematics and the laws of quantum mechanics, and it collapses in less than a second. The core, which was previously the size of the Earth, implodes to a sphere roughly 20 kilometers across, a neutron star, or in the most extreme cases, a black hole. The outer layers of the star, falling inward at a significant fraction of the speed of light, rebound off this newly formed dense core and are expelled outward in an explosion that briefly outshines the entire galaxy containing it. This is a core collapse supernova. The energy released in those first few seconds exceeds the total energy output of the Sun across its entire 10 billion year lifetime, multiplied by a factor of several hundred. Most of that energy, approximately 99% of it, is carried away not by light but by neutrinos, ghostly particles that interact so weakly with matter that they pass through the entire Earth as if it were not there. The light from a supernova, the 1% of the energy that emerges as radiation, is still enough to be visible across billions of light years. When astronomers observe galaxies at cosmological distances and detect a sudden brightening, a point of light that was not there the previous night, shining as brightly as the galaxy itself, they are watching the death of a single star, one star ending visible across the observable universe. But these giants are not the stars we need to worry about when we contemplate the end of stellar light. They burn too fast, die too quickly, and are relatively rare. The universe does not have many of them, and the ones it has are already mostly gone. The most massive stars that could have formed in the early universe are largely absent today because the conditions that produced them, the low metallicity, the enormous primordial gas clouds, are gone. The universe is not making many blue giants anymore. The stars that will determine how long the light lasts are at the opposite end of the scale entirely. They are called red dwarfs, and they are the most common stars in the universe by an enormous margin. Approximately 70 to 75% of all stars in the Milky Way are red dwarfs. In the observable universe, they likely account for more than 3/4 of all stellar objects. They are small, typically between 8% and 40% of the Sun's mass, and dim, radiating primarily in red and infrared wavelengths. The least luminous of them shine with roughly 1/10,000th the luminosity of the Sun. They are so faint that not a single red dwarf in the entire Milky Way is visible to the naked eye from Earth, despite there being hundreds of billions of them, and they are almost indestructible by stellar standards. A red dwarf burns its hydrogen fuel so slowly, at such low temperatures and pressures, that its lifetime is not measured in billions of years but in trillions. A red dwarf with half the mass of the Sun will burn for approximately 80 billion years, roughly 6 times the current age of the universe. A red dwarf with 1/10 the Sun's mass will burn for perhaps 10 trillion years. The smallest red dwarfs, hovering near the lower boundary of what allows nuclear fusion to ignite at all, may sustain fusion for as long as 10 trillion to 100 trillion years. To feel the weight of that number, hold this image. The current age of the universe is 13.8 billion years. 1 trillion is approximately 70 times that. 10 trillion is 700 times the current age of the universe. The smallest red dwarfs will still be burning, fusing hydrogen into helium in their cores when the universe is 700 times older than it is today. Every dinosaur that ever walked the Earth, every ocean that ever formed, every continent that ever drifted, every civilization that has ever risen and fallen, all of it has happened in a cosmic eye blink, compared to the remaining lifespan of the dimmest stars currently burning in the sky. There is something almost melancholy in this. The universe's longest-lasting lights are its faintest ones. The stars that will outlive everything else are the ones so dim that no human eye has ever seen them directly. They burn in the infrared almost invisible, radiating a warmth so gentle that a planet orbiting close enough to be in their habitable zone would need to be almost touching the stellar surface. Proxima Centauri, the nearest star to our Sun, is a red dwarf. It will still be burning long after the Sun has expanded into a red giant, consumed its inner planets, and died. Our Sun, by comparison, is a middle-aged star with a modest future. It is approximately 4.6 billion years old and has roughly 5 billion years of hydrogen burning remaining. When it exhausts its core hydrogen, it will not explode. It is not massive enough for that. Instead, it will expand. Over the course of several 100 million years, it will swell into a red giant growing to perhaps 100 to 200 times its current radius. In doing so, it will likely engulf Mercury and Venus and will come close enough to Earth, if Earth still exists in its current orbit, to boil away the oceans and strip away the atmosphere. Eventually, the Sun will shed its outer layers in a slowly expanding shell of gas, called a planetary nebula, a structure of extraordinary beauty, glowing with ionized gas lit by the hot core within. What remains of the Sun's core will be a white dwarf, a dense Earth-sized sphere, composed mainly of carbon and oxygen, no longer fusing anything, radiating only the stored heat from its long life. It will be roughly as massive as the current Sun, but compressed into a volume roughly the size of Earth. A teaspoon of white dwarf material would weigh approximately 5 tons. At first, a white dwarf is extraordinarily hot, surface temperatures of 100,000 degrees Kelvin or more. It glows white, then yellow, then orange, then red, as it cools over billions of years. Given enough time, far more than the current age of the universe, a white dwarf will cool completely to what astronomers call a black dwarf, an inert, cold, dark sphere of crystallized carbon and oxygen floating silently in space, emitting no light at all. No black dwarf has ever been observed. None exists yet anywhere in the universe. The universe is not old enough. The cooling process takes longer than 13.8 billion years, and every white dwarf currently in existence is still warm enough to glow. But they are coming. In the far future, the remnants of every sun-like star that has ever existed will eventually cool into dark spheres, drifting through an increasingly lightless cosmos. The picture that emerges from all of this is a universe with a shape across time. Right now, we are in what astronomers call the Stelliferous Era, the age of stars. It began with the first stellar ignitions, roughly 100 million years after the Big Bang, and it will end when the last star burns out. Given the longevity of red dwarfs, that endpoint lies approximately 100 trillion years in the future. 100 trillion years. The number is so large that even the most expansive analogies begin to break down. But consider this one. If you represented the Stelliferous Era as the length of a football field 100 meters from one end to the other, then the current age of the universe, 13.8 billion years, would occupy less than 1/10 of the first centimeter from the starting line. We are not even in the early game. We are still on the opening step. And yet the Stelliferous Era is itself just a prelude to what follows. Within this vast era of stellar burning, the universe is already showing the signs of its own aging. The evidence is not hidden, it is written in the light. When astronomers look at galaxies across different distances, they are also looking across different times. Because light travels at a finite speed, a galaxy 10 billion light-years away appears as it was 10 billion years ago. We see the universe's past directly layered in distance, and what those observations show is a cosmos that was in its youth furiously productive and is now in its middle age slowing down. The peak of cosmic star formation, as mentioned, occurred roughly 10 billion years ago. The galaxies of that era were brighter, bluer, more irregular and more active than the galaxies of today. They collided more frequently because the universe was smaller and denser, and collisions trigger star formation by compressing gas clouds into the density required for gravitational collapse. The early universe was loud, in the metaphorical sense, full of events, full of energy being released, full of new things being made. Today's universe is quieter. The large galaxies have mostly settled into stable rotating structures. The rate of galactic collisions has decreased. The gas that fuels star formation is being depleted. The Milky Way, a relatively large spiral galaxy, forms perhaps a handful of new stars each year. The elliptical galaxies, the older, rounder, redder galaxies that formed when smaller galaxies merged, have largely stopped forming stars altogether. Their gas was exhausted or expelled long ago. There is a classification that astronomers use that carries an almost elegiac quality when you understand what it means. Galaxies are often described as either blue cloud galaxies or red sequence galaxies. Blue cloud galaxies are actively forming stars. They are blue because new stars are hot and blue, and their light dominates the galaxy's color. Red sequence galaxies have largely stopped. They are red because the blue stars have already died, leaving only the cooler, redder, longer-lived stars behind. A galaxy moves from the blue cloud to the red sequence when it exhausts its star-forming gas, and the universe as a whole has been moving from blue to red for billions of years. The Milky Way is in transition. It sits, astronomically speaking, in the region between the blue cloud and the red sequence, what astronomers call the Green Valley. It is neither young nor dead. It is aging, gradually running out of the gas it needs to make new stars. In a few billion years, barring the infusion of new gas from the merger with Andromeda, it would likely complete its transition to the red sequence entirely. And Andromeda itself, that great spiral galaxy visible to the naked eye on clear nights, containing 1 trillion stars approaching at approximately 110 kilometers per second, will provide a temporary reprieve. When the two galaxies collide and merge several billion years from now, vast clouds of gas will be compressed. A burst of new star formation will briefly light the resulting galaxy with billions of new blue stars. The merged system, whatever name future beings give it, will experience something like a second youth, a final flowering of stellar birth before the gas runs out for good. But even that reprieve is temporary. The gas will be consumed, the new stars will burn and die, and the merged galaxy will settle eventually into a large, quiet, elliptical system, red, and aging its star-forming days behind it. Beyond that, there are the red dwarfs still burning, still fusing, still producing light for trillions of years. The universe's last stars will be its dimmest ones, small, cool red, burning with a patience that borders on the geological. If there is life anywhere in the universe in the far future, and we have no way of knowing whether there is, it will almost certainly be orbiting one of these faint embers, huddled close to a dim warmth in an increasingly dark and empty cosmos, looking out at a sky that contains far fewer lights than the sky above you tonight. The universe is not dying quickly. It is dimming slowly, the way a fire dims not with a sudden extinguishing, but with a gradual exhaustion of fuel, each log burning lower than the last, the light growing warmer and redder and weaker over hours until at last the coals glow faintly in the dark and then without drama go cold. The last star, almost certainly a red dwarf, small and dim and ancient beyond reckoning, will burn out approximately 100 trillion years from now. When it does, the Stelliferous Era will end. There will be no announcement, no event visible across the cosmos. One star will simply stop fusing. Its core will cool, its light will fade, and then for the first time since the universe was 3,800,000 years old, there will be no stars burning anywhere. What comes after that is something the human mind is not built to hold, but we are going to try. Before we move into the darkness that follows the death of the last star, it is worth pausing here in the present, in the still luminous universe, to feel the weight of what we have already described. You are alive in the Stelliferous Era, the era of stars, the era defined by nuclear fire burning in the cores of hundreds of billions of galaxies across 2 trillion galaxies worth of observable universe. You live in a cosmos currently producing light on a scale that will never be exceeded, that is already past its peak, and that will never return to this richness once it has gone. The light you see when you look at the sky tonight is not ordinary. It is not guaranteed. It is the product of specific conditions, a specific age of the universe, a specific state of its matter and energy that will not recur. The stars above you are burning because the gas that formed them compressed at the right time, under the right conditions in a universe young enough to still have the raw material required. That universe is aging, the raw material is depleting. The conditions are changing. Every night that you look up at a sky full of stars, you are seeing something that the universe will not offer forever. In 100 trillion years, the sky above whatever world might still exist will be dark. Not the dark of a cloudy night or the dark between stars. A genuine total permanent dark. No points of light from active fusion. No blue-white brilliance from young massive stars. No soft orange glow from sun-like stars in their middle age. No faint red warmth from the dimmest dwarfs. Nothing. The era you are living in this moment, this civilization, this capacity to look up and ask questions exists inside the light, inside the warmth, inside the brief extraordinary window when the universe still burns. That is not a small thing. That is everything. The last red dwarf has burned out. 100 trillion years have passed since the Big Bang. The Stelliferous Era is over. Take a moment with that sentence. 100 trillion years. The current age of the universe is 13.8 billion years. 100 trillion is roughly 7,000 times that number. If you compress the entire Stelliferous Era into a single day of 24 hours, the current age of the universe, with all of its history, all of its galaxies, all of its stars and planets and civilizations and extinctions, would occupy the first 2 seconds after midnight. Everything that has ever been observed through every telescope ever built by human hands happened in those first 2 seconds. The remaining 23 hours and 58 minutes belong to the slow, patient burning of red dwarfs in an increasingly empty cosmos. And now that day is over. What remains is not nothing. That is the first and most important thing to understand about what comes next. The universe after the last star does not become empty. It does not collapse or explode or vanish. It continues. The same laws of physics that governed the formation of galaxies and the fusion of hydrogen in stellar cores continue to operate precisely as before in a universe that now contains no active stars at all. The structures are still there. The remnants are still there. The forces are still there. What is gone is the light. What remains in the era that cosmologists call the Degenerate Era is a cosmos populated by the cold bodies left behind by stellar death, white dwarfs, neutron stars, black holes, brown dwarfs, objects that formed from collapsing gas clouds but never quite accumulated enough mass to ignite fusion, hovering in the dark, like failed stars cooling slowly toward the temperature of the surrounding space. And planets, billions upon billions of planets now frozen, now dark, orbiting nothing, drifting silently through a universe that has no warmth left to offer them. To understand what a white dwarf is in this context, not as an astronomical object described in a textbook, but as a presence in the post-stellar universe, you need to feel its scale correctly. When a star like our Sun exhausts its hydrogen and passes through its red giant phase, shedding its outer layers in a planetary nebula, what remains is a core of carbon and oxygen roughly the size of the Earth. This object contains approximately half to 60% of the original star's mass, compressed into a volume roughly 1 million times smaller. The material inside a white dwarf is not gas, not liquid, not solid in the ordinary sense. It is a state of matter called electron-degenerate matter, in which electrons are packed so tightly together that quantum mechanical effects, specifically the Pauli exclusion principle, which forbids any two electrons from occupying same quantum state, create a pressure that supports the object against further gravitational collapse. A white dwarf does not burn. It does not fuse. It is not a star in any active sense. It is the cooling remnant of one radiating the thermal energy stored from its previous life, losing heat to the surrounding space at a rate determined entirely by the temperature difference between its surface and the environment around it. When the last red dwarf burns out, and the Degenerate Era begins, the universe still contains an enormous number of white dwarfs, the remnants of every sun-like star that ever lived and died throughout the Stelliferous Era. These objects are cooling. They have been cooling, some of them for hundreds of billions or trillions of years already. Their surfaces, once blazing at hundreds of thousands of degrees Kelvin, have been dropping steadily. By the time the Stelliferous Era ends, the oldest white dwarfs will have cooled to temperatures of a few thousand degrees, still warm, still faintly glowing in the infrared, but producing almost no visible light. The cooling continues. over the next several quadrillion years, numbers so large that they require scientific notation to write conveniently roughly 10 to the power of 15 years, the white dwarfs continue to radiate heat into space. Space itself in this era is extraordinarily cold. The cosmic microwave background that ancient radiation left over from the first moments of the universe continues to cool as space expands. By the time the Stelliferous Era ends, the background temperature of the universe has already dropped from 2.73 Kelvin to a value far colder. As the Degenerate Era progresses and the universe continues to expand, the background temperature falls toward values vanishingly close to absolute zero. The white dwarfs are radiating into a near-perfect cold. A white dwarf cooling in such an environment is like a hot coal dropped into an ocean of liquid nitrogen. The heat differential drives the cooling rapidly at first, then more slowly as the temperature difference narrows. As the white dwarf approaches the temperature of its surroundings, the cooling slows to a crawl. It takes longer and longer to lose each additional degree of heat. The process is asymptotic. The white dwarf approaches the background temperature without ever quite reaching it, at least not in any finite time that can be conveniently described. Eventually, after timescales in the range of 10 to the power of 15 years, a quadrillion years, roughly 100 times longer than the entire Stelliferous Era, the white dwarfs will have cooled to the point where they are no longer warm enough to emit any meaningful radiation. They become black dwarfs, cold, dark, inert spheres of crystallized carbon and oxygen floating through the void at whatever temperature the universe happens to be at that moment, which is extraordinarily close to absolute zero. A black dwarf is one of the strangest objects that physics predicts, but that no human instrument has ever observed because none have had time to form. Think of it as a diamond the size of a planet. The carbon atoms inside a cooling white dwarf, as the temperature drops far enough, begin to organize themselves into a crystal lattice. The process is called crystallization, and it has actually been observed in white dwarfs using data from the Gaia Space Telescope, which detected a population of white dwarfs that appeared to be releasing latent heat during the crystallization process, a kind of stellar heartbeat in the long dying. The most massive white dwarfs crystallize first because their higher internal pressures favor the formation of crystalline structure at higher temperatures. When a white dwarf crystallizes completely, it is in the most literal sense a giant diamond. A diamond roughly the size of the Earth, containing approximately half the mass of the Sun, cold, dark and inert, floating in the void. If you could hold it, it would feel smooth and impossibly heavy. It would look like a black sphere, absorbing whatever faint radiation remained in the universe around it, reflecting nothing, emitting nothing. The remnant of a star that once burned bright enough to warm a planet, now indistinguishable from the darkness around it. The universe in the Degenerate Era will eventually be filled with these objects, quadrillions of them drifting through the dark, the remnants of every star that ever burned in the Milky Way and Andromeda, in every galaxy in the local group, cold, silent, still. But white dwarfs are not the only objects populating the Degenerate Era. The more massive stars, those that ended their lives not in gentle planetary nebulae, but in the violence of supernovae, left behind different remnants. Neutron stars are perhaps the most extreme objects in the universe that are not black holes. When a massive star's core collapses in a supernova, if the remaining mass falls within a certain range, roughly between 1.4 and approximately 3 solar masses, the collapse does not produce a black hole. Instead, the electrons and protons in the collapsing material are forced together under immense pressure, combining through a process called inverse beta decay to form neutrons. The result is an object composed almost entirely of neutrons packed together at nuclear density perhaps 20 kilometers in diameter, and containing 1 to 2 times the mass of the Sun. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. The density inside a neutron star approaches the density of an atomic nucleus, which is itself so densely packed that if you could remove all the empty space from the atoms in the human body, the resulting object would be smaller than a grain of sand while still containing the same mass. A neutron star is like that, but for an object containing more mass than the Sun. Neutron stars are born spinning fast. When the iron core of a massive star collapses from a body roughly the size of the Earth to a sphere 20 kilometers across the conservation of angular momentum, the same physical principle that makes a figure skater spin faster when they pull their arms inward accelerates the rotation enormously. Newborn neutron stars can spin hundreds of times per second. They are nature's most precise clocks. Their rotation so stable that some of them are used by astronomers as timing references more accurate than many atomic clocks. They also slow down over time as they lose energy by emitting radiation in a process tied to their powerful magnetic fields. Pulsars, the subset of neutron stars, whose beams of radiation sweep past Earth like a cosmic lighthouse, gradually lose rotational energy and slow over millions of years. Eventually, on timescales of billions to trillions of years, the rotation slows enough that the pulsar mechanism switches off. The neutron star becomes a cold, dark, spinning object, no longer beaming, no longer visible, gradually cooling toward the temperature of the surrounding universe. In the Degenerate Era, the neutron stars join the white dwarfs in their slow cooling. They are smaller and more exotic, but their fate is similar. Over immense timescales, they radiate their thermal energy into space, cooling toward the background temperature. The neutron star's crystalline neutron matter loses heat asymptotically. Like the white dwarfs, they approach but never quite reach the temperature of the universe around them, at least not before other processes intervene. Scattered among these remnants are the planets. In the Degenerate Era, there are still planets, not the same planets, orbiting the same stars, because the stars are gone. But the planets and the rocky debris of planetary systems persist. When a sun-like star passes through its red giant phase, it expands and may engulf its inner planets. But the outer planets typically survive, pushed to somewhat larger orbits by the mass loss from the dying star, then left to continue orbiting the cooling white dwarf. For a time, perhaps for billions of years after the white dwarf forms, these planets continue their orbital dance. The white dwarf is still warm enough to provide faint warmth, though it is nothing like the warmth of the original star. Gradually, as the white dwarf cools, the warmth fades. The planets grow colder. Their atmospheres, if they had any, have long since been stripped away or frozen to their surfaces. Their oceans, if they ever had ocean, froze in the first cold darkness after the star's death. Over trillions of years, they orbit their cold, dark stellar remnants in a silence so complete that the word silence seems inadequate. But even this arrangement does not last forever. On timescales of tens of quadrillions of years, the orbits of planets become unstable through a process called orbital decay driven by gravitational radiation, the emission of gravitational waves, tiny ripples in spacetime caused by orbital motion of any two massive objects around each other. This effect is extraordinarily small for ordinary planetary orbits, but given enough time it adds up. Over periods measured in 10 to the power of 20 years, that is 100 quintillion years, roughly 10 million times the length of the entire Stelliferous Era planets, orbiting white dwarfs and neutron stars will slowly spiral inward and eventually fall into their host object, releasing a brief pulse of energy before going dark forever. Some planets, those in wider orbits, will not spiral inward. Instead, they will be gradually ejected from their systems entirely through gravitational interactions with other passing objects. Over similar timescales, stars in galaxies, or rather the dark remnants of stars in the merged aged galaxies of the Degenerate Era, undergo similar processes. Gravitational interactions between the objects in what were once galaxies gradually transfer energy between them. Some objects gain energy and are ejected from the system entirely. Others lose energy and spiral inward toward the central mass concentration. This process, sometimes called the evaporation of galaxies, takes place over timescales of approximately 10 to the power of 19 to 10 to the power of 20 years. Roughly 90% of the stellar remnants in what was once a galaxy will be ejected into the intergalactic void, or rather, the interremnant void, since there are no longer any galaxies in the luminous sense. They drift away into an expanding universe, moving apart from one another at whatever velocity they were given in that long-ago gravitational interaction, cooling dark forever separated from everything else. The remaining 10% or so will spiral inward toward whatever massive black holes lie at the centers of the former galaxies. Over these immense timescales, even this slow, inward spiral produces a trickle of gravitational energy, almost imperceptible but real. The central black holes grow very slightly as they accrete these cold remnants, and then the universe enters a phase defined not by cooling white dwarfs, but by something altogether more exotic. There is one more process operating during the Degenerate Era that deserves mention because it is both strange and important. It is called proton decay, and whether it actually occurs is one of the great unresolved questions of particle physics. The standard model of particle physics, the best description of the fundamental constituents of matter that science currently possesses, predicts that protons, the positively charged particles at the heart of every atomic nucleus, stable. They do not decay. They persist indefinitely. But extensions of the standard model, including most grand unified theories that attempt to incorporate gravity alongside the other fundamental forces, predict that protons are not truly stable. They should decay after an extraordinarily long time into lighter particles. The predicted proton lifetime varies by theory, but most estimates place it somewhere above 10 to the power of 34 years. Current experimental limits from detectors buried deep underground to shield them from cosmic ray interference have established that if protons decay, their half-life is at least 10 to the power of 34 years, and possibly much longer. We have never observed a proton decay, but absence of observation is not the same as impossibility. If protons do decay, the consequences for the Degenerate Era are profound. By the time 10 to the power of 37 to 10 to the power of 40 years have passed timescales that make the Stelliferous Era look like a single heartbeat, every proton in the universe will have decayed. Every white dwarf, every black dwarf, every neutron star, every frozen planet, every cold rock and grain of dust and isolated atom drifting through the dark, all ordinary matter, every baryon in the universe, will have dissolved. The products of proton decay, primarily positrons and pions, which themselves decay into photons and neutrinos, will disperse into the surrounding space. If this happens, the Degenerate Era ends not with a specific event, but with a dissolution. Ordinary matter simply ceasing to exist over these unimaginable timescales, leaving behind only photons, neutrinos, and black holes. If proton decay does not occur, if protons are truly stable, then the black dwarfs and neutron stars will persist. They will drift through an increasingly empty and cold universe, orbiting nothing, cooling toward the temperature of the expanding void, potentially for timescales approaching 10 to the power of 100 years or beyond. They will not disappear. They will simply drift cold and silent in a darkness so profound and so ancient that the word ancient loses its meaning. Either way, the Degenerate Era leads to the same destination, a universe in which the dominant objects are no longer cold stellar remnants, but something far stranger. Objects from which nothing, not even light, can escape. Black holes. The black hole era is coming, and its timescales will make everything we have discussed so far look like the opening line of a story that takes a very long time to tell. But before we go there, hold this image for a moment. Somewhere in the Degenerate Era, perhaps 10 to the power of 15 years from now, perhaps longer, there is a planet. It was once like Earth. It orbited a star like the Sun. The star is long dead, its remnant a black dwarf, cold and dark, providing no warmth, no light, no radiation of any kind, detectable by whatever might once have lived on that planet's surface. The planet itself is frozen to a temperature within a few degrees of the cosmic background, whatever that temperature happens to be, at such an immense age of the universe. The planet is still there, still orbiting. The mountains are still mountains, though after quadrillions of years even they have changed rocks, flow like glaciers given enough time. Even at low temperatures and over such immense durations, the planet's surface has smoothed, reshaped, lost every feature that once characterized it. There are no oceans because all water is locked in ice, so cold it barely vibrates. There is no atmosphere. There is no magnetic field because the planet's core has long since solidified and stopped rotating relative to the mantle. There is nothing there that any instrument we currently possess would recognize as interesting. And yet, that planet exists. The atoms that once composed whatever life might have existed on its surface are still there, locked into minerals and ice, part of the bulk composition of a frozen world in an orbit that will itself eventually decay. Those atoms, carbon, oxygen, nitrogen, iron, were forged in the cores of stars that existed before this planet's sun was born. They will outlast the Degenerate Era itself, whether dissolved by proton decay or ejected into the void by gravitational interaction. They were never destroyed, only transformed, only carried forward in new configurations through the endless cold of a universe, still moving, still expanding, still unfolding according to its laws. That continuity is the one thing the universe does not abandon even in the deepest dark. The Degenerate Era ends. The stellar remnants have cooled, decayed, or been ejected into the void. Whatever ordinary matter remains is locked into objects so cold and so dark that the universe around them is indistinguishable from emptiness. The cosmic background temperature has fallen to values so close to absolute zero that the difference is academic. The universe is not quite at its coldest possible state, but it is close enough that the distinction barely matters to anything that might still exist within it. What remains scattered across the expanding dark are black holes. Not many of them relative to the scale of the universe. Not glowing, not active in any visible sense, not surrounded by the brilliant accretion disks of infalling gas that make them spectacular objects in the astronomical observations of the Stelliferous Era. Just black holes. Dense concentrations of mass so extreme that the curvature of space-time around them closes on itself, creating regions from which nothing, no particle, no photon, no signal of any kind can escape. They float in the dark like the universe's final punctuation marks, patient, silent, waiting, and slowly, imperceptibly evaporating. To understand what happens to black holes in the black hole era, you have to understand a prediction so strange, so counterintuitive, so contrary to everything that the phrase black hole suggests that when Stephen Hawking first published it, in 1974, many of his colleagues assumed he had made a mistake. Black holes radiate, not in any conventional sense, not by emitting light from a hot surface the way a star does, not by reflecting radiation from somewhere else. They radiate thermally from their event horizons through a mechanism rooted in quantum mechanics that has no classical analog and no intuitive explanation in everyday terms. Hawking himself described the derivation as the most beautiful calculation he had ever done. The result carries his name, Hawking radiation. To grasp the mechanism, you first need to know something about the quantum vacuum. Empty space in quantum field theory is not actually empty. It is filled with quantum fields, mathematical structures that permeate all of space-time, and these fields are never at rest. They fluctuate, constantly producing pairs of virtual particles and antiparticles that pop into existence and almost immediately annihilate each other, returning their borrowed energy to the vacuum. This process happens everywhere all the time, in every region of space, including the region just outside a black hole's event horizon. Normally, these virtual particle pairs annihilate before they can have any physical effect. But at the event horizon of a black hole, something different can happen. If a virtual particle pair forms right at the boundary, one particle can fall across the event horizon into the black hole while the other escapes. The escaping particle becomes real. It carries actual energy away from the black hole. And because energy must be conserved, the black hole pays the price. Its mass decreases by a tiny amount with each particle that escapes. The black hole is losing mass, slowly, unimaginably slowly for large black holes, but losing it nonetheless. This is Hawking radiation. The escaping particles have a thermal spectrum. They are emitted as if the black hole has a temperature called the Hawking temperature, which is inversely proportional to the black hole's mass. A more massive black hole has a lower Hawking temperature. A less massive black hole has a higher one. The largest black holes in the universe have Hawking temperatures so close to absolute zero that they are effectively undetectable against the current cosmic background radiation. The black hole is colder than the universe around it, and it actually absorbs more radiation than it emits, growing very slightly rather than shrinking. But the universe is cooling, the cosmic background temperature is falling, and eventually After the Stelliferous Era ends, after the Degenerate Era runs its course, after the universe has expanded and cooled for timescales that dwarf everything that has come before, the cosmic background temperature will drop below the Hawking temperature of even the most massive black holes. At that point, the balance shifts. The black holes begin to emit more energy than they absorb. They begin at last to shrink. Let us put numbers to this, because the numbers are where the full strangeness lives. A black hole with the mass of our sun has a Hawking temperature of approximately 60 billionths of a Kelvin. It is unimaginably cold, radiating energy at a rate so slow that the power output is a tiny fraction of a watt. To evaporate such a black hole completely through Hawking radiation would require approximately 10 to the power of 67 years. That is a number written as the digit 1 followed by 67 zeros. The entire Stelliferous Era, 100 trillion years, the age at which the last star burns out, is 10 to the power of 14 years. The time required to evaporate a solar mass black hole is 10 to the power of 67 years. That means the evaporation time for a solar mass black hole is longer than the entire Stelliferous Era by a factor of 10 to the power of 53. The Stelliferous Era fits into the evaporation time of a solar mass black hole, roughly as many times as the diameter of a proton fits into the distance from the Earth to the edge of the observable universe. And solar mass black holes are small. The supermassive black holes at the centers of galaxies are another matter entirely. Sagittarius A, the black hole at the center of the Milky Way, has a mass of approximately 4 million solar masses. The black hole at the center of the galaxy M87, the one famously imaged by the Event Horizon Telescope in 2019, the first direct image ever obtained of a black hole's shadow, has a mass of approximately 6.5 billion solar masses. Some of the most extreme black holes known to exist have masses of tens of billions or even tens of hundreds of billions of solar masses. The evaporation time of a black hole scales as the cube of its mass. Double the mass of a black hole and its evaporation time increases by a factor of 8. The evaporation time of Sagittarius A is approximately 10 to the power of 87 years. The evaporation time of the M87 black hole is somewhere around 10 to the power of 99 years. The most massive black holes in the universe, those that formed from the mergers of many smaller black holes throughout the Degenerate Era, growing as they consumed stellar remnants, may have evaporation times approaching 10 to the power of 100 years. That last number has a name. It is called a googol, a 1 followed by 100 zeros. It is a number so large that it exceeds the number of atoms in the observable universe by roughly 80 orders of magnitude. If you tried to write it out at the scale of 1 digit per Planck length, the smallest meaningful unit of length in physics, approximately 10 to the power of negative 35 meters, the number would be longer than the observable universe, is wide by an incomprehensible margin. And yet, given enough time, every black hole will evaporate. As a black hole evaporates through Hawking radiation, its mass decreases. As its mass decreases, its Hawking temperature increases. As its temperature increases, it radiates more intensely. The process is a feedback loop that begins unimaginably slowly and accelerates toward its conclusion. For most of a black hole's evaporation time, the vast majority of those 10 to the power of 67 or 10 to the power of 100 years, nothing much seems to happen. The black hole loses mass at a rate so slow that the change over any time period that humans have words for is negligible. But in the final stages, things change. As the black hole shrinks to smaller and smaller masses, its Hawking temperature climbs. When it reaches a mass comparable to a large asteroid, perhaps 10 to the power of 12 kilograms, its temperature has climbed to around 1 trillion degrees Kelvin, and it is radiating enormously. In its final second of existence, a black hole releases energy comparable to millions of nuclear weapons. A brief intense burst of gamma rays and other high-energy radiation, the last gasp of an object that has spent longer than a Google years quietly evaporating in the dark. Then it is gone. Not gone in the sense that something has been destroyed. The energy it radiated does not vanish. It disperses into the surrounding space as photons, neutrinos, and various high-energy particles which themselves decay or scatter and contribute to the slowly growing entropy of the universe. The information about what fell into the black hole, every particle, every atom, every remnant of every star that ever crossed its event horizon, may or may not be preserved in some encoded form in the radiation that escapes. This question, known as the black hole information paradox, remains one of the deepest unresolved problems in theoretical physics. Hawking spent decades arguing that the information was lost. Later in his life, he changed his position, suggesting it might be preserved in some subtle way in the outgoing radiation. The question is still open. But regardless of what happens to the information, the black hole itself ceases to exist. The event horizon shrinks to zero. The singularity, if singularities are even physically real, which is itself an open question, disappears. The space-time curvature that defined the black hole smooths out. Where there was once an object containing millions or billions of solar masses, there is now only a fading glow of high-energy radiation dissipating into an expanding universe. Consider what the universe looks like at this moment. At the moment the last black hole evaporates, somewhere around 10 to the power of 100 years after the Big Bang. The universe is unimaginably vast. Space has been expanding for that entire duration, and the scale of the observable universe, if such a concept even has meaning anymore, given that any observer would be completely isolated, is so large that even light years are an impractical unit of measurement. The temperature of the universe is so close to absolute zero that the difference from absolute zero is a number with hundreds of zeros after the decimal point before the first significant digit appears. There are no stars. There have been no stars for 10 to the power of 86 years or more, a duration so long that the entire Stelliferous Era is less than a rounding error. There are no white dwarfs, no neutron stars, no planets, no atoms, assuming proton decay has occurred. If protons are stable, there may be cold black dwarfs still drifting somewhere in the void, but they are so isolated, so cold, so far from everything else, that they are effectively indistinguishable from the nothing around them. There are no black holes. The last one has just finished evaporating its final burst of radiation, spreading outward at the speed of light, dispersing into a universe too cold and too empty to absorb it meaningfully. What remains? Photons, neutrinos, perhaps gravitons, perhaps some exotic relic particles from the early universe, if any survived the Degenerate Era. Gravitational waves, perhaps echoing from the final evaporation events. The quantum fields that permeate space-time, still fluctuating, still producing and annihilating virtual particle pairs as they always have, and the expansion of space, still expanding, always expanding. This is the threshold between the black hole era and what comes after. It has a name too. Cosmologists call it the Dark Era, and it is by the measure of any time scale that has preceded it the longest chapter of the universe's story by an unimaginable margin. Before we step into the Dark Era, it is worth asking a question that might already be forming at the edge of your awareness. It is a question that sounds simple but reaches very deep. Why does any of this matter? The universe will end in the sense that the structures we recognize, stars, galaxies, planets, black holes, will eventually cease to exist. The light will go out. The warmth will dissipate. The ordered configurations of matter that give rise to complexity, to chemistry, to life, and thought will dissolve into a cold, diffuse, featureless expanse. If that is the trajectory, if that is the destination, then what is the significance of anything that happens along the way? It is a question that has no easy answer. But consider this. The universe is approximately 13.8 billion years old. The black hole era will last until approximately 10 to the power of 100 years. On that scale, the Stelliferous Era, the entire age of stars from the first stellar ignition to the death of the last red dwarf, is 10 to the power of 14 years long. That is a fraction so small, relative to the full duration of the universe's existence, that it defies ordinary description. Everything that has ever lived, thought, wondered, suffered, loved, or looked up at the night sky has happened within that fraction. Every civilization that has ever built anything, every mind that has ever formed a question, every observation that has ever been made of the cosmos, all of it compressed into the briefest possible window, the Stelliferous Era, the only era when the universe contains enough energy gradients, enough warmth, enough light to support the processes that give rise to complexity. Life, if it exists anywhere in the cosmos, is a phenomenon of the Stelliferous Era. It requires energy flowing from hot sources to cold sinks. It requires chemistry, and chemistry requires atoms, and atoms require temperatures cool enough for electrons to bind to nuclei, but warm enough for chemical reactions to proceed. It requires liquid water, or something like it, which requires a star nearby and a planet at the right distance. All of those conditions exist only when stars are burning. We live in the only era when any of this is possible. Not just the only era when it has happened, the only era when it can happen. The universe will spend the overwhelming majority of its existence, from roughly 10 to the power of 14 years to 10 to the power of 100 years, in states where life as we understand it is impossible. Cold, dark, empty of energy gradients, ruled by objects that emit nothing or almost nothing. The Stelliferous Era is the universe's one moment of warmth, its single window of light. The brief, extraordinary interlude between two darknesses, during which everything that could become aware became aware, looked at the stars, and wondered where they were going. You are here. In that window, the stars above you are still burning. That is not nothing. That is everything. The last black hole is gone. There was no ceremony, no final light visible across the universe, because the universe that remains has no eyes to see it, and no medium capable of preserving the memory of the event. The burst of gamma radiation from the final evaporation spread outward at the speed of light into a space so cold and so empty that the photons will travel, in all likelihood, forever, never absorbed, never scattered, simply propagating through an expanding void that grows larger with every passing moment. The universe continues. It has always continued. Continuation is perhaps the one thing it does without exception. But what continues now is not the universe that preceded it in any recognizable sense. There are no structures. There are no concentrations of mass. There are no gradients of temperature or energy that could drive any process, any reaction, any event that would be recognizable as an event to any observer that might once have existed. The universe has arrived, or is arriving, at what physicists call maximum entropy, the state in which energy is distributed as evenly as possible across the available space, the state in which no further useful work can be extracted from any process, the state in which nothing in the thermodynamic sense can happen. This is the dark era. Entropy is a word that appears often in discussions of the universe's fate, and it is worth being precise about what it means, because the common understanding that entropy means disorder, that the universe is becoming more chaotic, captures something true but misses something important. In thermodynamics, entropy is a measure of the number of ways a system can be arranged while still appearing the same from the outside. A gas compressed into one corner of a room has low entropy. There are relatively few ways to arrange those molecules in that small space. The same gas spread evenly throughout the room has high entropy. There are an enormous number of ways to arrange the molecules such that the gas appears uniformly distributed. The second law of thermodynamics states that in any closed system, entropy tends to increase over time. Systems evolve from less probable states toward more probable ones, and the most probable state for most physical, the universe taken as a whole, is a closed system. Its entropy has been increasing since the Big Bang, and it will continue to increase until it reaches its maximum possible value for its current configuration. At that point, no further increase is possible, because no further reorganization of energy is available to drive any process. The universe reaches thermal equilibrium with itself, every region at the same temperature, every quantum field at its lowest energy state consistent with the current expansion. Nothing happens. Nothing can happen. This state has a name in physics. It is called the heat death of the universe. The phrase is slightly misleading because the universe at heat death is not hot. It is as cold as it is possible to be while still not being at absolute zero. The vacuum energy prevents it from reaching perfect stillness. But the cold is so extreme and so uniform that it functions as a kind of death in the thermodynamic sense. Not a violent ending, not a collapse, not an explosion. simply the cessation of all processes, the universe falling silent in the most complete way imaginable. The physicist Lord Kelvin first articulated this concept in 1851, deriving it from the second law of thermodynamics, which had only recently been formalized. He described it as a state of universal rest and death. Later physicists refined the picture, but the essential conclusion has not changed in the century and a half since. If the universe expands forever and the second law holds heat, death is the eventual destination. There is no mechanism known to physics that prevents it. In the dark era, what remains are photons and neutrinos, and the faint residue of Hawking radiation from the long evaporated black holes. These particles travel through expanding space, their wavelengths stretching as the universe grows, their energies declining towards zero. The photons that once carried starlight, once illuminated planets, once triggered the chemical reactions of photosynthesis and vision and photography, these photons are still traveling, but their energy has been redshifted to such extreme degrees that calling them photons with any useful energy seems almost an overstatement. The neutrinos are even more ghostly. They interact so weakly with matter that they pass through planets and stars and galaxies almost without effect when matter existed. Now, in a universe without matter, they travel freely through the void, their energies also declining with the expansion approaching but never quite reaching zero. The quantum fields are still there. They were always there underlying everything, and they persist. The vacuum energy, the lowest possible energy state of the quantum fields, is non-zero. Space is not perfectly empty in the quantum mechanical sense. Virtual particles continue to appear and annihilate, as they always have, as they always will. The universe at heat death is not a perfect void. It is a quantum mechanical vacuum, which is the closest thing to nothing that physics permits. And in that quantum mechanical vacuum, something strange becomes in principle possible. It requires a very long time, longer than anything we have discussed so far, if such a comparison is even meaningful when the numbers involved are so extreme that they cannot be compared in any intuitive sense. But given enough time and time in the dark era, is the one resource that exists in unlimited supply. The random fluctuations of the quantum vacuum can in principle produce spontaneous fluctuations of unusual size. The argument runs as follows. In quantum field theory, the vacuum is not a static state, but a dynamic one constantly fluctuating. Most fluctuations are tiny, the creation and annihilation of virtual particle pairs at the smallest scales. But in a universe of infinite extent, with infinite time available, fluctuations of any given size will eventually occur. Given enough time, timescales so incomprehensibly large that 10 to the power of 100 years looks like an opening remark, the vacuum could spontaneously fluctuate into a state that contains a localized region of low entropy, a small bubble of organized matter, a brief local reversal of the arrow of time. Physicists sometimes call these Boltzmann brains, a sardonic reference to the 19th century Austrian physicist Ludwig Boltzmann, who first seriously grappled with the implications of statistical mechanics for the long-term fate of the universe. A Boltzmann brain is a hypothetical self-aware structure that arises spontaneously from a random fluctuation in the quantum vacuum, a brief, improbable, but not physically prohibited condensation of matter and energy into something organized enough to have a momentary experience before dissolving back into the surrounding equilibrium. Boltzmann himself found the implications deeply troubling. If the universe exists for long enough, and if consciousness can arise from any sufficiently organized structure, then random fluctuations should eventually produce conscious observers in far greater numbers than the observers produced through the ordinary process of cosmological evolution, galaxy formation, stellar nucleosynthesis, planetary chemistry, and biological evolution. The number of Boltzmann brains that would arise through random fluctuation in the dark era would, under some calculations, vastly exceed the number of ordinarily evolved observers that existed during the Stelliferous Era. This leads to a philosophical problem, sometimes called the Boltzmann brain paradox. If you are more likely to be a Boltzmann brain, a random fluctuation with false memories of an ordered universe, than an ordinarily evolved observer, then you have reason to doubt whether your observations of an ordered universe are real. The fact that you seem to observe consistent physical laws, a coherent history, and a universe that makes sense might be statistically less probable than simply being a fluctuation that happens to have those experiences momentarily. Most physicists resolve this paradox not by taking Boltzmann brains seriously as a description of likely observers, but by treating the abundance of Boltzmann brains as a sign that something is wrong with the underlying cosmological model, a cosmology that predicts vastly more random fluctuation observers than ordinarily evolved observers is in some sense making a prediction that undermines its own credibility. This tension is one of several reasons why some physicists suspect that the universe's long-term fate may be more complex than the simple heat-death scenario suggests. But these are theoretical speculations. What the physics firmly predicts is the following. The universe in the dark era will spend an effectively infinite amount of time in a state of maximum entropy with quantum fluctuations, the only events occurring, and those events producing both nothing permanent, nothing persistent, nothing that accumulates into structure or complexity. There is another concept worth examining here, one that operates on timescales even more extreme than the Boltzmann brain argument, and that touches the boundary between physics and philosophy in a way that is difficult to categorize as either. It is called the Poincaré recurrence theorem. Henri Poincaré was a French mathematician and physicist of extraordinary breadth working in the late 19th and early 20th centuries. Among his many contributions to mathematics and physics, he proved a theorem about the behavior of dynamical systems governed by deterministic physical laws over infinite time. The theorem states that any bounded system with finite energy evolving according to deterministic laws will eventually return to a state arbitrarily close to any previous state given sufficient time. In plain language, if you wait long enough, the universe will spontaneously reorganize itself into a configuration that looks to any arbitrarily chosen degree of precision like any previous configuration, including configurations that look like a young low-entropy universe, including configurations that look like the universe as it exists right now. The Poincaré recurrence time for the observable universe, the time after which a recurrence becomes statistically likely, is a number so large that writing it in standard scientific notation provides almost no intuitive handle on its magnitude. The recurrence time is approximately 10 to the power of 10 to the power of 10 to the power of 56 years. This is not a number that can be compared to anything else discussed in this journey. It is not just larger than 10 to the power of 100 years. It is incomparably, unimaginably, categorically more enormous. The Google year evaporation time of the largest black holes is to the Poincaré recurrence time, as a single atom is to the observable universe. And yet the theorem holds, in principle. If the universe is truly finite in phase space, if the number of possible states it can occupy is truly finite, then recurrence is not just possible. It is certain. The caveats are enormous. The universe may not be bounded in the required sense. An eternally expanding universe with infinite extent may have infinite phase space, in which case the Poincaré recurrence theorem does not strictly apply. Quantum gravitational effects at extreme timescales may change the rules in ways that current physics cannot describe. The assumption of deterministic evolution may break down at the quantum level in ways that prevent true recurrence. These are not trivial objections, but the concept itself, the idea that given enough time even the most improbable configurations become not just possible but inevitable, carries a weight that is difficult to dismiss entirely. It suggests that the arrow of time, the relentless increase of entropy that defines the thermodynamic direction of the universe's evolution, is not absolute. It is statistical. On ordinary timescales, entropy increases because there are overwhelmingly more high-entropy states than low-entropy ones, and random evolution tends toward the most probable. But given infinite time, the improbable becomes certain. On Poincaré recurrence timescales, the universe is not dying, it is waiting. There is one more possibility that belongs in this territory, and it sits at the outermost edge of what current physics can address. It is not a prediction in the usual sense, but a framework, a way of thinking about the universe's long-term fate that some cosmologists find more compelling than heat death precisely because it does not lead to a permanent ending. It is the idea of eternal inflation and the multiverse. In the inflationary model of the early universe, the rapid exponential expansion that smoothed the cosmos in its first fractions of a second was driven by a quantum field, the inflaton field, that was temporarily in a high-energy state and then decayed to its ground state, releasing its energy as the particles and radiation of the early universe. In some versions of inflationary theory known as eternal inflation, this process does not stop everywhere at once. In most regions, inflation ends and the familiar universe forms. But in other regions, quantum fluctuations cause the inflation to continue. Space in those regions keeps expanding exponentially, spawning new pockets of ordinary spacetime as inflation ends locally within them. In this picture, our observable universe is one bubble in an eternally inflating background. Other bubbles have formed, are forming, and will form, each one a separate universe with potentially different physical constants, different laws, different histories. The multiverse is not a prediction in the sense that it can be directly tested with current technology, and some physicists regard it as metaphysics rather than physics. But it is a natural consequence of the most widely accepted versions of inflationary theory, and it has serious proponents among working cosmologists. If eternal inflation is real, then the heat death of our universe is not the heat death of everything. The inflationary background continues, new universes form. Some of them may have conditions that allow for complexity, for stars, for chemistry, for life. The ending of our particular bubble does not end the process of universe formation. But this offers cold comfort in a specific sense. Those other universes, if they exist, are not accessible to us. They are separated from our bubble by an expanding inflationary background that no signal can cross. Whatever happens in those other universes, whatever complexity arises, whatever observers form, whatever light burns in those other skies, it is permanently beyond our reach. Our universe still ends. Our stars still go dark. Our black holes still evaporate. Our dark era still extends across timescales that make the Stelliferous Era a vanishing fraction of the whole. The multiverse, if real, is an answer to the question of whether something continues. It is not an answer to the question of whether we continue. In the dark era, in the silence that follows the evaporation of the last black hole, there is a quality to the stillness that has no analogue in the Stelliferous Era. During the age of stars, silence was always relative. There was always something happening somewhere. A supernova detonating in a distant galaxy, a red dwarf quietly fusing hydrogen in a stellar nursery, a planet completing one more orbit around its aging sun. Even in the deepest void between galaxies, the cosmic background radiation was present. Ancient photons still carrying information, still connecting the present to the moment of last, scattering 3,800,000 years after the Big Bang. In the dark era, that connection is severed. The photons from the cosmic background have been stretched by the expansion of space until their wavelengths are longer than the observable universe itself. A concept that barely holds meaning, but is the direction toward which the physics points. The information they once carried is not gone exactly. Energy is conserved. Information, at least in some theoretical frameworks, is conserved, but it is distributed across scales so large, in configurations so diffuse, that the word information seems to have lost its ordinary meaning. The universe in the dark era is not empty in the sense that a room is empty. A room is empty of objects, but full of air and light and the possibility of events. The universe in the dark era is empty in a deeper sense. Empty of gradients, empty of processes, empty of the conditions required for anything to happen that could be described as an event in the ordinary sense of the word. And yet it persists. Space continues to expand. The quantum vacuum continues to fluctuate. Time, if time still has meaning in this context, a question that some physicists regard as genuinely open, continues to pass. If there is a final question in this territory, it is not what happens to the universe. It is what the universe's ending means for the things that existed within it, for the stars that burned, for the planets that formed, for the chemistry that organized itself into living systems, for the minds that arose from that chemistry and looked outward and asked questions. Does their having existed matter if the universe forgets them? The universe does not have a memory in any conventional sense. There is no record being kept, no ledger in which the history of the Stelliferous Era is preserved. The photons from the last stars will eventually be redshifted to zero energy. The gravitational waves from the mergers of the last black holes will eventually be stretched to wavelengths longer than the universe. If proton decay occurs, the last atoms will eventually dissolve. Even if protons are stable and black dwarfs persist, they drift in such isolation, so cold, so dark, so separated from everything else that they carry no information that any observer could ever access. The universe does not remember. It does not mourn. It does not in any sense that physics can describe care. And yet the question of whether it matters stands apart from the question of whether the universe preserves a record. The stars burned, the planets existed, the minds arose, those things happened. The fact that the universe will eventually reach a state in which no trace of them remains does not retroactively unmake them. The past is the one thing that cannot be changed, not by entropy, not by expansion, not by the evaporation of black holes or the dissolution of matter. What happened happened, permanently, irrevocably, beyond the reach of any process of erasure. The light from a dead star, the photons that left its surface thousands of years ago and have been traveling through space ever since, are real. They are moving through the universe right now. The fact that they will eventually be stretched to zero energy does not unmake the moment of their emission, the nuclear reactions that produced them, the star that burned for billions of years to generate them. Existence, even temporary existence, is not nothing. That may be the most important thing the Dark Era teaches, precisely because it is a place from which nothing can return, nothing can persist, nothing can remember. In the absolute silence of maximum entropy, the question of what it means to have existed becomes as clear as it is ever going to get. It meant exactly what it was, while it lasted. Step outside tonight if you can, or simply close your eyes and imagine it. The air is cool, the ground beneath you is solid. Above you the sky is dark, in the way that skies are dark on clear nights. Not an absolute darkness, but a darkness punctuated by light. Stars scattered across the vault of the heavens in their thousands, each one a point of fire suspended in the void, each one burning with the same essential process that has driven stellar light since the universe first ignited its first suns. Hydrogen falling inward under gravity, pressure building at the core, temperature climbing until the nuclei of hydrogen atoms are moving fast enough and are close enough together that the strong nuclear force can bridge the gap between them. Fusion, energy released. Light propagating outward through the stellar interior over thousands of years before finally escaping the surface and traveling at 3,000,000 kilometers per second across the darkness toward you. You are standing in that light right now. Ancient light, most of it. Light that left its source before you were born, before your parents were born, before any human civilization existed in any form. And you are receiving it through two small organs on the front of your skull, converting it through photochemical reactions into electrical signals and experiencing it as beauty. This is what the journey to the end of the universe returns you to. Not abstraction, not equations. This, the specific, irreplaceable, unrepeatable fact of a human being standing under a burning sky. You know now what that sky actually is. You have traveled through it in the only way available to us, through thought, through the mathematics of physics, through the implications of what we have measured and calculated and extrapolated toward the horizon of the knowable. You have seen where it goes. You have seen the shape of the story from beginning to end as far as physics can trace it. The Stelliferous Era, 100 trillion years of stellar burning beginning in the dark aftermath of the Big Bang and ending with the death of the last red dwarf. The only era in which the conditions for complexity, for chemistry, for life, for awareness can exist anywhere in the universe. An era that is, from the perspective of the universe's total duration, a vanishingly brief flash of light between two immensities of dark. The Degenerate Era, the long cooling of the remnants, white dwarfs fading to black dwarfs, neutron stars slowing and going cold, planets drifting from their orbits and dissolving into the void. Ordinary matter, either decaying through proton decay or persisting in cold, dark, isolated spheres, drifting through a universe that has forgotten how to be warm. The black hole era, the last structures, the final concentrations of mass. Black holes evaporating through Hawking radiation so slowly that the process makes the death of stars look instantaneous, each one losing mass in increments so small that quadrillions of years pass between any two moments that could be meaningfully distinguished. Until the last one, the largest one, radiates its final burst of gamma rays into an empty universe and disappears. Statum entropy, the quantum vacuum fluctuating endlessly, photons and neutrinos traveling through expanding space with energies declining towards zero, no events in the thermodynamic sense, no process, no gradient. The universe in its final state, not destroyed, not collapsed, not ended in any violent sense, simply present in the most diffuse and featureless and permanent way imaginable. The long silence at the end of everything. You know all of this now. You have looked at the end of the universe and held it in your mind, as clearly as the human mind can hold such things. And now look up again. Look at the stars. They look different now, do they not? Not different in the sense that they have changed. The light arriving at your eyes is the same light it always was, photons produced by nuclear fusion, traveling for years or centuries or millennia before reaching you. The stars are in the same positions they were before you began this journey. Orion stands where it has always stood from your vantage point. The planets trace the same paths through the ecliptic. The Milky Way, if your sky is dark enough to show it, spills across the same arc it has always crossed. But you are different. Your relationship to what you are seeing is different, because now you understand what it means for those stars to be there. You understand what conditions had to be met, what sequence of events had to unfold across 13.8 billion years for this particular moment to contain burning stars visible from a living planet. The universe had to begin in a state of low entropy, a state so improbable that our best physics cannot explain why it began that way, rather than in a state of higher entropy. The laws of physics had to be precisely calibrated to allow for the formation of atoms. Had the fundamental constants been slightly different, hydrogen would not have formed, and without hydrogen there are no stars. The early universe had to contain the right distribution of density fluctuations to seed galaxy formation fluctuations, so small, 1 part in 100,000, that their origin is traced to quantum events in the first fractions of a second. Galaxies had to form and evolve and collide and merge over billions of years, building up the heavy elements required for rocky planets and organic chemistry. A particular star had to form in a particular part of a particular galaxy with a particular complement of planets, one of which happened to be at the right distance to maintain liquid water on its surface. On that planet, chemistry had to organize itself into self-replicating structures, and those structures had to evolve over 4 billion years through an essentially open-ended process of mutation and selection, producing eventually a species capable of asking questions about its own origin. And that species had to develop over a few thousand years of intellectual history. The mathematics and the instruments and the conceptual frameworks required to look outward and inward simultaneously to measure the distance to galaxies and the temperature of the cosmic background and the curvature of space-time and the evaporation rate of black holes, and to synthesize all of those measurements into a coherent picture of where the universe came from and where it is going. Every one of those steps was necessary. The absence of any one of them would have meant that this moment, this specific exchange of information, this particular awareness reflecting on its own existence and its place in the story of the cosmos would not have occurred. The odds against this specific moment are in any ordinary probabilistic sense incomprehensible. And yet, here it is. Here you are. There is a quality to the present moment that the journey through cosmic time clarifies rather than diminishes. It is easy when confronted with the scale of the universe, its age, its size, its indifference to the existence of any particular planet or species or mind, to feel that individual existence is negligible, that the warmth of a human life measured against the cold arithmetic of 10 to the power of 100 years amounts to nothing worth the name. But that response misunderstands the geometry of value. The universe does not measure significance by duration. If it did, the Stelliferous Era, the only era that can contain anything resembling experience or meaning, would itself be negligible, being so brief compared to what follows. The Dark Era, which contains nothing, would be the most significant era of all, simply by virtue of lasting the longest. That conclusion is absurd, and its absurdity reveals the flaw in the reasoning. Duration is not significance. The length of time something lasts tells you nothing about whether it matters. What matters, if anything matters, is the quality and depth of what occurs during the time something lasts. A single afternoon of genuine understanding, one moment of real clarity about what the universe is and where it came from, is not made less valuable by the fact that it ends. The ending is not a subtraction from what preceded it. The ending is simply the end. The stars above you tonight are burning with energy that will sustain this planet for billions of years. The sun is halfway through its main sequence, life still young enough that its light has been warming Earth's surface for billions of years, and will continue to do so for billions more. The air you are breathing was produced by organisms that have been processing sunlight and carbon dioxide for hundreds of millions of years, building up the oxygen concentration of the atmosphere to the level that allows complex animals to exist. The ground beneath your feet contains the compressed remnants of ancient seafloors, ancient coral reefs, ancient forests, each layer a record of the life that preceded you on this planet. You are not standing outside the story of the universe. You are standing inside it at one of its richest and most improbable moments, when the conditions for complexity are fully developed, when the universe's creative period is still producing stars and planets and chemistry and awareness, when the full archive of cosmic history is still accessible to anyone patient enough to look. In 2 trillion years, a hypothetical observer in the local group will look out at a sky nearly empty of external galaxies. In 100 trillion years, the last stars will be dying. In 10 to the power of 100 years, the last black holes will evaporate. But right now, tonight, in this moment, the sky above you contains the light of 2 trillion galaxies, each containing hundreds of billions of stars, each star a nuclear furnace producing energy at rates that dwarf everything human civilization has ever generated. Right now is the peak, or close enough to it that the difference on cosmic timescales does not matter. The knowledge of the universe's ending does not darken the present sky. If anything, it illuminates it. When you know that the stars are temporary, that they burn through finite fuel at finite rates toward inevitable extinction, they become more remarkable rather than less. A candle burning in a dark room is not diminished by the fact that its wax is finite. The light it produces is real. The warmth it radiates is real. The shapes it carves out of the darkness are real. The fact that it will eventually go out does not unmake any of those things. It simply means that the light is precious in a way that an eternal light could never be, because an eternal light would carry no information about its own nature. It would simply be a temporary light burns with a history of fuel being consumed, of energy being converted from one form to another, of a process that began at a specific moment and will end at a specific moment. The stars are like that. Each one is burning its particular fuel at its particular rate, on its particular journey from ignition to extinction. The sun has been burning for 4.6 billion years and has roughly 5 billion left. The dim red dwarf nearest to us will burn for another few trillion. The most massive blue giants burning in young stellar nurseries right now will be gone in a few million years, their deaths seeding the next generation of stars with the heavy elements forged in their cores. Every star is a story with a beginning, a middle, and an end, and the light that star produces during its life is not diminished by its ending, it is defined by it. The same is true in whatever way the comparison holds for everything else that exists within the Stelliferous Era. For planets, for chemistry, for the organisms that arise from that chemistry, for the minds that arise from those organisms. Each one is a temporary configuration of matter and energy organized by the same physical laws that govern stars and galaxies, burning through its own fuel in its own way, producing its own particular form of complexity and order before returning its matter and energy to the larger flows of the universe. The ending is not the meaning, but it is inseparable from it, because it is precisely the temporariness of the flame that makes the light visible. There is a question that belongs at the end of a journey like this one. Not a scientific question, those have been answered as fully as physics currently allows. A human question, perhaps the oldest human question. What should we do with this? With the knowledge that the universe has an ending, that the stars will go dark, that the warmth we depend on is borrowed from a process that is at every moment consuming itself toward an inevitable conclusion, that we live in the briefest of windows, the Stelliferous Era, the single flash of light between two infinities of dark, and that this window, extraordinary as it is, will close. There is no single answer. There is probably not a complete answer, but there is a direction. Look up, not as an escape from the knowledge of impermanence, not as a way of ignoring what the physics says, but as an act of recognition, of presence, of deliberate attention to what is actually there above you right now in this moment of the universe's history that will not come again. The light arriving at your eyes tonight left its sources at various moments across the last few thousand years. Some of it is younger than recorded human history. Some of it is older than the pyramids. Some of it departed its source before human beings had fully developed the cognitive structures required to notice it as something separate from the background noise of existence. All of it traveled through the universe to reach you. That is not a small thing to have happen on a given night. It is in fact one of the more extraordinary things that the universe currently arranges on billions of planets, around billions of stars moment by moment across the 2 trillion galaxies that still fall within our observable horizon. The universe is generous with its light for now. Be generous with your attention. There is a star in the constellation Boötes called Arcturus. It is one of the brightest stars in the northern sky, a giant star in its old age, burning orange and steady on clear evenings above the horizon. The light arriving at your eyes from Arcturus tonight left its surface approximately 37 years ago. It has been traveling through the vacuum of space at 3,000,000 kilometers per second, crossing a distance of roughly 350 trillion kilometers. Since before many of the people reading these words were born, that light was already in transit, when certain technologies we now consider old were still considered new, when certain conflicts that now feel historical were still unresolved, when the universe was 37 years younger than it is tonight. It arrived, at your eye, at this moment. Of all the directions that light could have traveled, and it traveled in all of them, simultaneously spreading outward from Arcturus in a sphere growing at the speed of light, some small fraction of it happened to intersect with the position of a planet orbiting a particular star at the precise moment when a particular being happened to be oriented in the direction of the source, with eyes open in conditions dark enough to see. The universe does not aim its light. It simply produces it in all directions, and whatever it happens to illuminate is what gets illuminated. The fact that you are here to receive it is not something the light intended. It is something the universe, through 13.8 billion years of its own unfolding, happened to arrange. That arrangement is temporary. Everything about it is temporary. The planet will not always be here. The star will not always be burning. The species standing on the planet will not, in all likelihood, persist for anything approaching the full duration of the Stelliferous Era. And the Stelliferous Era itself, as we have seen, is a brief window between two darknesses, so vast and so complete that no analogy from ordinary human experience can adequately describe them. But the light is here now, and so are you. We have traveled a long way together in this journey, from the burning sky of the present through the slow dimming of the Stelliferous Era, as star formation rates declined and galaxies aged from blue to red, through the death of the last red dwarf 100 trillion years from now, and the onset of the Degenerate Era, the long cooling of white dwarfs into black dwarfs, the slowing of neutron stars, the gradual dissolution of planetary systems through orbital decay and gravitational ejection, through the black hole era dominated by the patient evaporation of the universe's final structures through Hawking radiation over timescales approaching a Google years 10 to the power of 100, numbers so large that the entire age of stars is less than a rounding error at their beginning, and into the dark era itself, the universe at maximum entropy, quantum fields fluctuating in the cold, photons traveling through expanding space with energies declining towards zero, no events, no processes, no gradients remaining to drive any further change. We have looked at the end of the universe as clearly as physics currently allows, and we have found that the end, when examined, honestly does something unexpected to the present. It makes it luminous. The philosopher and physicist Ernst Mach once wrote that the goal of science is not to explain nature, but to describe it, to give the mind the most economical possible account of what the senses actually encounter. There is wisdom in that restraint, but there is also something that pure description misses. Because when you describe the universe at the level of detail that modern cosmology achieves, when you trace the trajectory of matter and energy from the first fractions of a second after the Big Bang to the final evaporation of the last black hole, you are not just cataloging facts. You are encountering something that the facts taken together produce. You are encountering the improbability of right now. Every observation we have made of the universe confirms that it began in a state of extraordinarily low entropy. The Big Bang was not a random explosion in any ordinary sense. It was an initial condition of exceptional order so extreme that the subsequent 13.8 billion years of increasing entropy have still not dissipated it entirely. The stars still burn because the universe's initial order is still being consumed. The chemistry that supports life still operates because the energy gradients created by that initial order are still steep enough to drive complex processes. We are, in the most literal thermodynamic sense, living off the interest of an investment made at the beginning of time. The low entropy of the Big Bang is the principle from which all subsequent structure, all galaxies, all stars, all planets, all chemistry, all life, all thought ultimately derives. We do not know why the universe began in such a low entropy state. It is one of the deepest unresolved questions in cosmology, touching the boundary between physics and the philosophy of origins. But the fact that it did is the reason anything exists that could ask the question. The universe gave itself a beginning that made complexity possible. And then it ran for 13.8 billion years, producing layer after layer of increasing structure and intricacy, until it arrived at a moment in which a species on a small planet around an ordinary star could look outward at the full extent of what had been produced and recognize it for what it been produced was. That recognition is not an accident. It is not an afterthought. It is what the universe looks like from the inside at this particular point in its history. Not all of the universe, the vast majority of the universe, has no awareness and no capacity for it. But here, in this small corner, in this specific arrangement of matter and chemistry and evolution, the universe has produced something that reflects on itself. You are the universe looking at itself. That is not a metaphor. It is a physical description. The atoms in your brain were forged in stellar cores. The energy driving your thoughts came ultimately from nuclear fusion in the sun. The information encoded in your nervous system was assembled through 4 billion years of biological evolution on a planet that formed from the same cloud of gas and dust that formed the sun. You are a local concentration of the universe's matter and energy organized by its laws into a structure capable of modeling the universe itself. When you think about the cosmos is thinking about itself through you. That capacity, the capacity for the universe to know what it is, exists only in the Stelliferous Era. Only when stars are burning, when chemistry is possible, when the energy gradients are steep enough to drive biological processes. In the Degenerate Era, there is no chemistry. In the black hole era, there is no matter organized into anything resembling biology. In the dark era, there is nothing that could be called awareness in any sense that the word has ever been used. The Stelliferous Era is not just the era of stars, it is the era of knowing, the only era in which the universe can be comprehended by anything within it, and that era is now, right now. This moment with its burning sky and its ancient light, and its small figures standing on a cooling planet looking outward into a darkness that they have against all probability learned to read. The last light of the universe will not be dramatic. There will be no final supernova, no concluding detonation, no event visible across the cosmos. It will simply be the last photon from the last evaporating black hole, dispersing into the expanding void, its wavelength stretching as space grows, its energy declining towards zero until it is indistinguishable from the quantum noise of the vacuum itself. No one will see it. There will be nothing left to see it with. But that last photon will have a history. Every photon does. It will have been produced ultimately by the same process that produced the first photons to escape the early universe, the conversion of mass into energy, governed by the same physical law that Einstein derived in 1905 at a patent office in Bern, working from first principles in the margins of the paperwork that filled his days. The last photon of the universe will be, in some sense, a descendant of the first, connected to it through an unbroken chain of physical cause and effect, stretching across 10 to the power of 100 years. Between the first photon and the last, everything else that we know of occurred. The formation of hydrogen and helium, the assembly of galaxies, the ignition of stars, the synthesis of heavy elements in stellar cores and supernova explosions, the formation of planets, the emergence of chemistry, the origin of life, the 4 billion years of evolution that produced, among countless other things, this species, curious, short-lived, cosmically insignificant in size, remarkable in its capacity to ask questions about things far beyond the reach of its senses. That is the story. The whole story as far as we can tell. A universe that began in extraordinary order, burned through that order for an unimaginable span of time, producing layer upon layer of complexity, and will eventually arrive at a state of maximum disorder from which no further complexity can arise. We are in the middle of that story. Or rather, we are near the very beginning of it, in the one chapter where anything happens that could be called interesting. We are in the light. Go outside tonight, or stand at your window, or simply hold the sky in your mind as you have been holding it throughout this journey. The stars above you are burning. They have been burning for billions of years. They will burn for billions more, or in the case of the smallest red dwarfs, for trillions. The light they produce crosses distances that reduce all human measures to irrelevance, and arrives at a planet with liquid oceans and a breathable atmosphere, and billions of living things arranged into ecosystems of staggering complexity. And some of those living things have eyes that can receive that light, and minds that can ask what it means. The universe arranged all of that. Not intentionally, the universe has no intentions. But through its laws, its constants, its initial conditions, it produced a sequence of events that led here to this, to you standing beneath a burning sky, with the knowledge of what those fires are and where they are going. The warmth you feel from the sun during the day, from the planet's stored heat during the night, is the warmth of nuclear fusion happening 150 million kilometers away. It left the sun 8 minutes ago. It crossed the void. It arrived at your skin. It is real. It is here. It is now. The Degenerate Era is 10 to the power of 14 years away. The Black Hole Era ends in 10 to the power of 100 years. The Dark Era extends beyond that into timescales that have no names adequate to them. All of those dark chapters are coming in the sense that physics predicts them, and nothing currently known to science can prevent them. But they are not here yet. The stars are still burning. The sky is still full of light. The universe is still in this window, in this extraordinary and temporary and unrepeatable Stelliferous Era, alive with the fires it set at its beginning. You are alive in the light of those fires. You are made of the ash of earlier ones. You carry in your body the products of supernovae that lived and died billions of years before the Earth existed, and you carry in your mind the capacity to know what that means. That is not a small inheritance. That is the universe at one of the most improbable moments of its entire history knowing itself. The darkness is coming. It is always coming, but it is not here yet. And the light, this light right now falling on this world in this moment of the universe's one burning era, is extraordinary. It is temporary, and it is ours.